Hello everyone, today we will look at some problems about a single pump and pipeline analysis. For the first problem, a pump delivers water from the reservoir A to the reservoir B, and we know HA equals 47.5 meter and HB equals 55.9 meter. And we know the length of the pipeline equals 1,650 meter, and diameter of this pipe equals 0.5 meter. And the Darcy Weisbach friction factor F equals 0.018. And ignoring the meta-analysis, we need to determine the flow rate and the velocity in the pipeline. And the problem also gave us the pump characteristics in this table. So we know the system head H sub SH equals the HS plus the HF. And for this system, we know the HS equals HP minus HA equals 55.9 meter minus 47.5 meter. So the HS equals 8.4 meter. And for the head loss, from the table 3.4 in the textbook, the Darcy Weisbach formula in the international unit system can be expressed as the HF equals K times Q square. And we also know the K value equals 0.0826 times the friction factor times the length of the pipe divided by the D to the power of 5. These two equations are on the table 3.4 in the textbook. And from the problem, we know the F, the friction factor, equals 0.018, and the length equals 1,650 meter, and the diameter of this pipe equals 0.5 meter. So we can determine the K value equals 68.5. And now we know the key value. And the problem also gave us the pump characteristics. So we can use the Excel to create a table like this one I created before. Oh, sorry. So we know the Q value, and we also know the key value equals 78.5. So we can use this equation, K times Q squared, to determine the head loss in this column. And then we can use this equation, HS equals HS plus HF, to determine the system head in this column. And then we can plot a system head in a figure like this one I also created before. So the blue curve is a pump characteristic curve, and the orange curve is a system head curves. And we can find that the intersection of the pump characteristic curve and the system curve is at the Q equals 0.75 cubic meter per second, and the HP, the required pump head, equals 52.6 meter. So we know the flow rate in the pipeline, so we can determine the velocity equals the Q the Q divided by the A, so equals the Q divided by the pi times d squared over the 4. So this value equals 0.75 cubic meter per second divided by the pi times 0.5 squared over the 4. So the value is, the velocity is 3.82 meter per second. So we have done this problem. For the second problem, in the transmission system shown in this figure, and we know the HA equals 100 feet and HD equals 150 feet, and the Darcy Weisbach friction factor is 0.02 for all the pipes, and pipe AB is 4,000 feet long with a diameter of 3 feet, and the pipe CD is 1,140 feet long with diameter of 3 feet too. And the branch BC1 has an length of 100 feet and diameter of 2 feet, and the branch BC2 is 500 feet long with diameter of 1 feet. And this problem also gave us the pump characteristics table, and we need to determine the system flow rate, pump head, and the discharge in branches 1 and 2. It is better to use the method of equivalent pipes to solve this problem, and we found the equivalent pipe to replace branch BC1 and BC2. And arbitrarily letting the DE equals 3 feet and FE equals 0.02. So now we know the square root of DE to the power of 5 divided by FE times LE equals square root of D1 to the power of 5 divided by F1 times L1 plus square root of D2 to the power of 5 divided by F2 times L2. This is equation 3.47 in the textbook. And from the problem, we know that the D1 equals 2 feet. The D1 is the diameter of the branch BC1. And the length of the BC1 U1 equals 100 feet. And we know the friction factor for all the pipe equals 0.02. And we also know the D2 branch, the diameter of branch BC2 equals 1 feet, and then L2 equals 500 feet, and F2 also equals 0.02. Since we also know the D, we're letting the DE equals 3 feet and FE equals 0.02, so we can get that the LE, the length of the equivalent pipe, equals 652 feet. And since we know the diameter of pipe AB and pipe CD are both 3 feet, so they are the same as the equivalent pipe diameter. So now the 3 pipes in series can be regarded as one pipe. So the total length of pipe between the reservoir A and the reservoir D, the total length equals the length of pipe AB plus the length of the equivalent pipe plus the length of the pipe CD. So we know the length of pipe AB equals 4,000 feet, and the LE equals 652 feet, and the length of pipe CD equals the 1,140 feet. So we know the total length of pipe between these two reservoirs equals 5,792 feet. And we also know H sub S, the system head equals the HS plus HF sub F. For this system, the HS equals HD minus HA equals 150 feet minus 100 feet. So the HS equals 50 feet. And similar to the previous problem from the table 3.4 in the textbook, the Darcy-Weisbach formula in the British unit system can be expressed as HF equals K times Q squared, and the K equals 0.0252 times F times L divided by the d to the power of 5. This equation, there's two equations also in the table 3.4 in the textbook. And from problem, we know the L equals 5,792 feet we determined before, and diameter of the pipe equals 3 feet, and the F equals 0.02. We can determine the K value equals 0.012. And now we know the key value, and we also know the pump characteristics, so we can use Excel to create a table like this one I created before. Yes, we know the Q, so use the equation HF equals K times Q squared. We also know the K, so we can determine the friction loss in this column, and then we can get the head loss. We can get the system head in this column, and then we can plot the system head in a figure like this one. So we can find that the intersection of the pump characteristics curve and the system curve is approximately at the Q equals 30.5 feet, and the HP equals 15.2 feet. Since we know the flow rate in the pipe. So now we can determine the friction head loss between the pipe BC. So HFBC equals 0.0252 times, times FE times LE divided by the DE to the power 5 times Q square. So now this value equals this 252.0252 times 0.02 times the length of BC. So the length of BC is now is the equivalent pipe of, so equals 652 feet divided by the 3 feet to the power of 5 times 13.5 cubic feet per second square. So we can now determine the friction loss between the BC equals 0.246 feet. And since branch 1 and since branch BC1 and branch BC2 are the parallel pipes, so we know the HFBC should equal to HFBC1 equals HFBC2. So for branch BC1, the head loss HFBC1 equals 0.246 feet equals 0.0252 times F1 times the L1. The L1 is the length of branch BC1 divided by the diameter of branch BC1 to the power of 5 times Q1 squared. Since we know F1 equals 0.02 and L1 equals the 100 feet and D1 equals 2 feet. So now we can determine the flow rate in the branch BC1. Q1 flow rate in the branch BC1 equals 12.5 cubic feet per second. Similar for the branch BC2. So the HFBC2 equals 0.246 feet equals 0.0252 times F2 times L2 divided by D to the power of 5 times Q2 squared, and F2 equals 0.02. The length of the BC2 equals 500 feet, and the diameter of the BC2 D2 equals 1 feet. So now we can determine that the flow rate in the branch BC2, so the Q2 equals 1.0 cubic feet per second. So we finish this problem. For the third problem, a 1.5 feet diameter pipeline conveys water from the reservoir A to reservoir B, and the length of pipeline is 13,800 feet, and the decibel back friction factor is 0.02, and the water surface in reservoir B is 196 feet higher than the variable A, and neglecting the minor losses, we need to determine the flow rate and energy head added to the flow by each pump, and if two identical pumps are used in series. And the problem also gave us the pump characteristics in this table. And we know the system head H sub SH equals H sub S plus HF. For this system, we know the HS equals HB minus HA. The value is 196 feet. Problem gave us. And similar to the previous problem, the Darcy Weisbach formula in the British unit system can be expressed as HF equals K times Q square, and the K equals 0.0252 times F times L divided by the D to the power of 5. And we know the length of the pipeline equals 30,800 feet. And the F equals 0.02. Diameter of this pipe equals 1.5 feet. So we can determine the K value equals 0.916. And we know the key value, and we also know the pump characteristics. So we can use Excel to create a new table. Like this one. But we need to note that since the two identical pumps are used in series, so the heads are doubled. And we know the discharge, and according to this equation, and we can determine the friction loss in this column, and according to this equation, and we can determine the system head in this column, and then we can plot the system head in a figure. And from the table, or from this figure, we can know the intersection of the pump characteristics curve and the system curve is at the Q equals 15 cubic feet per second, and the HP equals 402 feet. And since the two identical pumps are used in series, so each pump adds half of the energy head. So the HP1 equals 201 feet, and the HP2 also equals to the 201 feet. So we finish this problem. For this problem, a pump pipeline system delivers water from the reservoir A to B with HA equals 45.5 meter and HB equals 92.9 meter. And we know the length of this pipe equals 1,860 meter, and diameter of this pipe equals 0.5 meter. And the Darcy Weisbach friction factor F equals 0.02. And the minor losses include an inlet, exit, and the swing type check valve. And the problem also gave us the pump characteristics in this table. And when a single pump is used in the pipeline, the flow rate is 0.5 cubic meter per second with a pump head of 73 meter. And we need to determine the flow rate in the pipeline if two identical pumps are used in a parallel combination. And also we need to determine the flow rate in the pipeline if two identical pumps are used in a series combination. And for this problem, since we need to consider minor losses, so the system head H sub SH equals the HS plus the HF, the friction loss plus the minor losses. So KE plus the KD plus the KV times V squared over the 2G. This is a minor losses. And for this system, we know the HS equals HB minus the HA, so the value is 92.9 meter minus 45.5 meter. So we know the HS equals 47.4 meter. And similar to the previous problems, such we spec formula in the international unit system can be expressed as HF equals K times Q squared, and the K equals the 0.0826 times F times L over the D to the power of 5. This two is in the table 3.4 in the textbook. And from this problem, we know that L equals 1,816 meter, and the friction factor equals 0.02, and the diameter of this pipe equals 0.5 meters, so we can determine the K value equals 98.3. And for the minor losses, we assume the inlet is the square edge type, so the KE, the coefficient of entries, equals the 0.5, and the KD equals 1. And the problem also told us the valve is a swing type check valve. So the from textbook, we know the KV equals 2.5. And now we know the KE plus KD plus the KV equals 4. And when two pumps in series, and we can create the table like this one. And we need to know that the heads are doubled when the two identical pumps are used in series. And then we know the equation HF equals K times Q squared. The K we have determined before, and the Q is given to us, so we can determine the HF in this column. And we know the flow rate, so we can determine the velocity accordingly. So the velocity equals Q divided by the pi times d squared over the 4. So after determining the velocity, we also can calculate the minor losses. So the minor losses equals KE plus KD plus KV times V squared divided by 2G. This value we determined before is the 4. So we can calculate the minor losses in this column, and then we get the system head in this column. And then we plot the system head in a figure. And from the table, this row and the figure, we know the intersection of the pump characteristic curve and the system head curve is at the Q is approximately equal to 0.75 cubic meter per second, and the HP is approximately equal to 105 meter. This is for the two pumps in series, and when two pumps in parallel, we can create a table like this one. And we need to know that the discharge are doubled when two identical pumps are used in parallel. So similar to the previous equations, we can determine the HF in this column and the minor losses in this column and the system head in this column. We also can plot the system head in a figure like this one. And from the table, this row, and this figure, we can know the intersections of the pump characteristic curve and the system head curve. See that the Q is approximately equal to the 0.6 cubic meter per second, and the HP is approximately equal to the 85 meter. So we have done this problem. For this problem, a branching pipeline pump system is shown in this figure, and each pipe has the following properties: diameter equals 1 meter, the length equals 1,600 meter, and the friction factor F equals 0.02. And the two pumps are identical, and the pump characteristics are tabulated below in this table. And we know the water surface elevation in reservoir A is 26.2 meter, and in the reservoir D is 33.5 meter. And the discharge in the pipe BC is 500 liter per second in the direction from the B to the C. And we need to determine the discharge in AB and BD, and the water surface elevation in reservoir C, and we also need to determine the head added to the flow by each pump. So to determine the discharge in AB and BD, first we need to determine the system head for the pipeline going through the reservoir A to the reservoir C. So the system head HSH equals the HSAD plus the friction loss in pipe AB plus the friction loss in pipe BD. And from problem, we know the HSAD equals HD minus HA equals 33.5 meter minus 26.5 meter, 26.2 meter. So we know the HSAD equals 7.3 meter. And for the HFAB, similar to the previous problems, we know the HF equals K times Q square, and in the international unit system, the K equals 0.0826 times F times L over the D to the power 5. And we know the pipe length equals 1,600 meter, and the friction factor equals 0.02, and the diameter equals 1 meter. So we can determine the K value for the pipe AB equals 2.64. And for the HF BD and HF equals K times Q minus 0.5 squared. We need to know that the discharge in the pipe BD is reduced by the 0.5 cubic meter per second after the junction. Since we know the discharge in pipe BC is 500 liter per second, so it equals to 0.5 cubic meter per second. So after the junction, the discharge in the pipe BD is reduced by 0.5. That's why in this equation the Q need to minus 0.5. So the K also equals to the 0.0826 times F times L over D to the power 5. So also the pipe length equals 1,600 meter, and F equals 0.02, diameter equals 1 meter. So we can determine the K for the pipe BD also equals to the 2.64. And then we can create a table like this one. The problem gives us the discharge, and according to this equation, HAB, KAB times QAB square, we can determine the friction loss in the pipe AB in this column. And for the friction loss in the BD, so the equation is HF BD equals KBD times Q AB minus the 0.5 square. This is this column, the discharge is for the discharge in the pipe AB. The problem gave us. So according to this equation, we can determine the friction loss in pipe BD in this column. And we need to note that when the discharge in the AB less or equal to the 0.5 cubic meter per second, there is no flow in the pipe BD, so the friction loss in pipe BD is 0. Yeah, and then we can determine the system head in this column, and we can plot the system head in a figure like this one. Oh, sorry. Like this one. So we can determine the intersection of the pump characteristic curve and the system curve is at the Q AB approximately equals to 1.1 cubic meter per second, and the HP, the pump head in the AB, pipe AB, approximately equals to 11.5 meter. And therefore, we know the discharge in pipe BD equals the discharge in AB minus discharge in the BC. So the value is 1.1 cubic meter per second minus 0.5 cubic meter per second the problem gives us. So we can determine the QBD equals 0.6 cubic meter per second. And from the problem, the discharge in the pipe BC is 500 liter per second. So according to this table, we can know the pump head is 19 meter. So we know the HPBC equals 90 meter. So until now, we have determined the discharge in AB and BD. We know the QAB equals 0.1 cubic meter per second. The QBD equals 0.6 cubic meter per second. And we also know that the head added to the flow by the H pump, HP AB equals 11.5 meter, and the HP BC equals 90 meter. And we still need to determine the water surface elevation in reservoir C. So we balance energy between reservoir A and junction B. So the equation is that HA plus HP AB equals the EB plus the HFAB. The EB is the total energy had at junction B. So since we know the HA equals 26.2 meter and HPAB, the pump head in the pipe AB, equals the 11.5 meter we determined before, and the HFAB equals K times QAB square, so equals 2.64 times 1.1 square. So now we can determine that the EB equals 34.5 meter. And then we balance the energy between junction B and reservoir C. So equation is EB plus the HPBC, the pump head, in the pipe BC equals HC plus HFBC. And the total energy had at the junction B we have determined before. So the EB equals 34.5 meter. And we also determined HPBC equals 90 meter before. And the HFBC equals K times QBC square. So the value equals to 2.64 times 0.5 square. So we can determine that the water surface elevation in reservoir C, HC, equals 52.8 meter. So we have done this problem. For the last problem, we need to determine the discharge in each pipe. in this figure, and we know the HA equals 100 feet, and HB equals 80 feet, and HC equals 120 feet. And the problem also gave us each pipe's characteristics and the pump characteristics. And for this table, the problem gave us the pipe characteristics, and for this table, the problem gave us the pump characteristics. And from this figure, we can see the both pumps actually used in parallel and push flow through the pipe 3. So the pump characteristics of each pump can be added together as a parallel pump combination and superimposed on the system curve, so we can determine the total discharge and the flow contributions from each pump. Let's look at the pipe 1 and pipe 3 first. So for pipe 1 and pipe 3, we know that HP1 equals HSCA plus friction loss in pipe 1 and HF3, the friction loss in pipe 3. And we rearrange this equation and we get that HP1 minus HSCA minus HF1 equals HF3. So this is the net HP1. And the problem gave us the elevation of HC and HA, so we know this HSCA equals HC minus HA equals 120 feet minus 100, feet minus 100 feet. So we can get that HSCA equals 20 feet. And for the HF1, similar to the previous problem, HF1 equals K1 times Q squared, and in a British unit system, the Q equals 0.0252 times F times L over the D to the power of 5. And since we know the problem gave us the length of the pipe 1 equals 8,000 feet, and F1 equals 0.02, and diameter of pipe 1 equals 2 feet. So we can determine the K1 equals 0.126. And for pipe 2 and pipe 3, we know HP2 equals HSCB plus HF2, the friction loss in pipe 2, plus the friction loss in pipe 3. And we also rearrange this equation, so HP2 minus HSCB minus HF2 equals HF3. So this is a net HP2. From the problem, we know HSCB equals HC minus HB. So the value is 120 feet minus 80 feet. So we know the HSCB equals 40 feet. And HF2 equals K2 times Q squared, and K equals 0.0252 times f times L over the d to the power of 5. And from the problem, we know the answer of the type 2 equals, let me check, equals 9,000 feet. And f2 equals 0.02, and the diameter of pipe 2 equals 2 feet. So we can determine K2 equals 0.141. And for the friction loss in the pipe 3, similar to the previous problem, H3 equals K3 times Q squared, and we know the K equals 0.0252 times F times L over the D to the power of 5, and the answer of pipe 3 equals 15,000 feet, and F3 equals 0.02, and D3 equals 2.5 feet. So we can determine that the K3 equals 0.0774. And now we can use Excel to create a table like this one. Yeah. And the problem gave us the Q and HP1, so we can determine the net HP1 using this equation that we determined before. So the net HP1 equals HP1 minus HSCA minus HF1. So HSCA equals 20 feet, and HF1 equals K1 times Q squared, so equals 0.126 times Q squared. So we know the Q, so we can determine the net HP1 in this column. Also, we can determine the net HP2 in this column, since we know the net HP2 equals HP2 minus HSCB minus HF2, and we know the HSCB we determined before is 40 feet, and HF2 equals K2 times Q squared equals 0.141 times Q squared. So we can determine the net HP2 in this column. And for the friction loss in the pipe 3, HF3, we also know that the HF3 equals K3 times Q squared. So the K3 we have determined before is 0.0774 times Q squared. So according to this equation, we also can determine the HF, the friction loss in pipe 3 in this column. And then we plot the data in a figure like this one. The blue curve is a net HP1, and the orange curve is a net HP2, and the gray curve is friction loss HF in pipe 3, HF3. Since two pumps are used in parallel, so we added their discharge together at the same HP, so we can get the yellow line, the combined net pump curve. Now we can find that intersection of the combined net pump curve and HF3 curve is at total discharge at Q3. At Q3 approximately equals to 34 cubic feet per second, and a net pump had at HP approximately equals to 90 feet, and at the same head of 90 feet to pump 1 and pump 2 curve, we can read that 190 can read that the Q1 approximately equals to 22.5 cubic feet per second, and the Q2 approximately equals to 11.5 cubic feet per second. So we have done this problem.